Okay, let's look at an example of shielding, a graphical example, figure 8.3 in your book. So electrons in the same energy level lead to a slightly lower effective nuclear charge. And why is that? Well, the electrons are both negatively charged, so they repel each other. And when we look at helium, a helium atom here, we see that to remove one of the two electrons it has, it would take this much energy. Once one is already removed and there's only one electron left, that one electron that's left is much harder to remove because it's not feeling a repulsive force from a partner electron. Now let's look at how inner electrons shield outer electrons. So for lithium has 3 electrons. The electron in the 2s energy level is really easy to remove. And why is that? It's because these 2 inner electrons are shielding that nuclear charge from the outer electron very efficiently. So there's a much lower effective nuclear charge, and it has very small energy to remove that electron. And when we look at if both of those 1s electrons are removed and now we only have one electron in the 2s orbital, it's much harder to remove that because it's feeling a much higher effective nuclear charge because those 2 inner electrons are not there shielding. And your book gives this figure as well, talking about the penetration of an orbital and how that leads to orbital stability. So the closer an electron orbital gets to a nucleus, the more stable that orbital is, the lower the energy of that orbital, because the electron, the negatively charged electron, is closer to the positively charged nucleus, and they attract one another. And if we look at figure 8.4, the 1s is the most stable. It's the closest to the nucleus. But we see that the 2s is actually more stable than the 2p. And why is that? That's because of this part right here of the 2s orbital. It gets much closer, even if it's just a very small fraction of the orbital, it gets closer to the nucleus. So it penetrates closer. And penetration increases the attraction and decreases shielding. So each energy level is split into sublevels of different energy. And as we've seen, these splittings of energy levels are caused by penetration and shielding. So for a given n value, a given principal quantum number, a lower L value is going to have a lower energy sublevel. So the order of the sublevel energies is S, P, D, and F. Now if we look at, remember what those L values for those are, the L value of an S orbital is 0, 1, L value of 1 is a P, L value of 2 is a D orbital, and L value of 3 is an F orbital, just to remind you about the angular momentum quantum numbers. Right. For a hydrogen atom, the sublevels are all, for a given principal quantum number, they're all the same energy. So the 2s and the 2p are at the same energy level. 3s, 3p, and 3d are all at the same energy level. And why is that? It's because hydrogen only has one electron. But other orbital energy subshells don't follow that pattern for hydrogen, because every other atom has more than one electron. And this is a figure of the y-axis represents energy, and this is where all the sublevels lie with respect to one another. So it's similar to 8.5, figure 8.5 in your text. So within a given shell, that is, within a given principal quantum number, the subshells fill in the order of S, P, D to F. But as you can see up here, at higher N values, higher shell levels, subshells, there starts to be some overlap. And the classic example of that is the 4s orbital is actually lower energy and fills before the 3d orbital, the 3d orbitals. And we'll talk a little bit later about, I'll go back, we'll talk a little bit later about how you know the order of these, how to fill the orbitals. And you can see at the very top, the energy levels get really close to one another, and there's really not a very good way to predict where an electron's going to fill next. Okay, moving on to section 8.2. And we're going to talk about electron orbital diagrams and electron configurations. So this is an example of an orbital diagram, and it shows the different orbitals in relation to one another with energy on the y-axis. So the lower energy orbitals are shown lower. As you go up in energy, the orbitals go higher on the y-axis. And this particular orbital diagram is lithium. There's 3 electrons. How do we fill these orbital diagrams? Well, there's a couple rules we need to follow. The first is the Aufbau principle. This states the most stable atomic structures are those in which electrons are in the lowest energy orbitals available. Another way you can put that is electrons always add to the lowest energy orbital. So when you're adding, you always go for the lowest available orbital, the lowest energy available orbital. And there's a maximum of 2 electrons per orbital. That's the exclusion principle. We'll mention that again in a minute. The next rule is Hund's rule, and that states for degenerate orbitals, so for orbitals with the same energy level, the lowest energy configuration maximizes the number of unpaired electrons. And we're going to see examples of these 2 rules. So for hydrogen, if we consider hydrogen, it has 1 electron, and it's going to, by the Aufbau principle, it's going to go into the lowest energy orbital, which would be the 1s. Right, that's simple enough. Now when we consider helium, there's 2 electrons. So the first one again goes into the 1s orbital by the Aufbau principle. The second one goes into the 1s orbital, but it's opposite spin. So we can say that now the n equals 1 shell is filled. There's 1 orbital in the n equals 1 shell. That's the s orbital. and it contains 2 electrons of opposite spin. And that's what's known as the exclusion principle. The fact that no 2 electrons in a given atom can have the same 4 quantum numbers. So that limits the number of electrons per orbital to 2. Now let's look at some other continue on in the periodic table with lithium and beryllium. So here we see the orbital diagrams for hydrogen, helium, lithium, and beryllium. And these orbital diagrams are written sideways. That's just to save space. Remember that the energy levels of the 2s and the 2p are actually higher than the energy level of the 1s, as shown up here. But we're writing them horizontal to save space. So it's nice to write these orbital diagrams, but an easier way to do the same, convey the same sort of information, is to write electron configuration. How do we do that? That's listed here in this column. So hydrogen would be a 1s1. That means the principal quantum number equals 1. It's an s orbital, and it has 1 electron in that s orbital. Helium is a 1s2. Again, principal quantum number is 1. The orbital is s, so the L value is 0. And now there are 2 electrons in that orbital. Lithium, the 1s orbital is filled with helium. So now lithium, the next electron in lithium, moves to the 2s orbital. Lithium being 1s2, 2s1. And as you might guess, beryllium is 1s2, 2s2. Another way, a really helpful way when you're moving down further rows in the periodic table, is to use what are known as condensed configurations. And a filled shell can be represented by the nearest noble gas, or the previous noble gas in the row above the element you're looking at. So for lithium, that previous filled noble gas would be helium. And I should mention now that the noble gases, if you don't know, are in the far right-hand side of the periodic table in group 8A, so the last column of the periodic table. And they all, as we'll see here in a minute, they all have a filled valence shell. That's why they're called noble gases, because they don't react because their valence electron shells are filled. So the condensed configuration for lithium, we can write, instead of 1s2, 2s1, we can write helium in brackets followed by 2s1. And beryllium, similarly, will be helium 2s2. Now let's keep going into the next subshell, which would be the 2p. That starts with boron. Boron, we add 1 electron in the 2p orbital, and its condensed configuration becomes helium 2s2, 2p1. Carbon, 1 more electron. It becomes 2s2, 2p2. And nitrogen becomes 2s2, 2p3. And you notice how when we fill these 2p orbitals, we're using Hund's rule. So all 3 p orbitals have the same energy. They're degenerate. And the way to fill that is to have the electrons each fill separate orbitals until all 3p orbitals have at least 1 electron in them. Continuing on, we see that now with oxygen, fluorine, and neon, we start adding electrons of opposite spin to those orbitals. So we start adding paired electrons. And you can see the condensed configurations, we're just adding one p electron each time. And neon becomes 2s2, 2p6. That is actually a filled shell, so we can just write that as neon with brackets, because neon is in the last column of the periodic table. It's a noble gas. Again, you see the pairing of electrons until the 2p orbitals are all filled. So this brings up two different types of electrons. As we see when we've written the condensed configuration, there really are two different types. One are core or inner electrons, and those are in filled inner shells in an atom, and those are not involved in any chemistry. And next we have the valence electrons. Those are the outer electrons, and those are what really influence an atom's chemistry. And if we use fluorine as an example, its electron configuration is 1s2, 2s2, 2p5. Its core electrons would be that of the previous noble gas, which would be helium. So that would be the 1s2 electrons. And its valence or outer electrons would be 2s2, 2p5. So fluorine has two core electrons that aren't involved in the chemistry of fluorine, and 7 valence electrons. Now we can depict the orbital occupancy of atoms using the actual orbital shapes, and that's shown in figure 8.7 in your text. Just to remind you what shapes the s and the p orbitals actually have. We see the 1 electron in hydrogen. The blue becomes a little bit darker for helium because it has 2 electrons in that orbital, so that orbital is filled. Next, for lithium, we see the inner 1s electrons are filled. The 1s orbital is filled, and you have one more electron in the 2s. And you can just kind of work through this table if you'd like to see the actual orbital shapes. Now, one thing you should notice that in the periodic table, when you look at electron configurations, the atoms in a group or a column, they all have similar valence electron pattern. So group 1A all has one s electron, one valence s electron. Group 2A, they all have 2 valence s electrons. 3A, they all have 3 valence electrons. They're 2s2, 2p1, and so forth. And again, group 8A, the very far right of the periodic table, they're noble gases. They're filled shells. And another trick while looking at the periodic table, the row number. So row, so the row is also called the period, and that number is equal to n, the principal quantum number. So the first row, you all have a principal quantum number of 1. Second row, principal quantum number is now 2, and so forth. So this periodic table is really arranged based on electron configurations. Let's look further now through the fourth row, the fourth period. We see potassium. Its condensed configuration is argon 4s1, calcium 4s2. Now with scandium we start adding d electrons. So we get 4s2 3d1, titanium 3d2, vanadium 3d3, and then we get to chromium, and this is where we see a deviation in the trend. Instead of 4s2 3d4, we now fill 4s1 3d5 for chromium. And then manganese, we're back to the same pattern. So we go back to 4s2 3d5. Okay, this all follows, again, the same pattern until we get to copper. And now copper, there's another deviation. We go 4s1 3d10 instead of 4s2 3d9. So these are very important deviations in the rules that you should remember. And why is that? Well, chromium and copper, they don't follow this pattern. And it has to do with the special stability that's formed when there's a half-filled or completely filled D sublevels. So that D shell, that D subshell, is very stable when it's half-filled or completely filled. And it's stable enough that it takes an electron away from the 4s orbital, to fill or half-fill the D subshell. So if we look at the pattern that we fill orbitals with, we can see that here's a figure that shows you the order: 1s to 2s to 2p, 3s, 3p. There's another figure here that your book gives. If you can remember this, it might help you. I tend to think this is a little confusing, but it might help some people. But what I really like using is just the periodic table itself. And here's a figure that shows that. You got, just by counting, you know that those are 1s, these will be 2s, 2p, 3s, 3p, 4s. Again, the row you're in is the principal quantum number until you get to the transition metals. Then we go 4s to 3d. So the d is always going to be n minus 1. So the row number minus 1, followed by 4p, 5s, 4d, 5p, 6s. Now with the f, your number is going to be n minus 2. So we're in the 6th row, so the f's actually going to start at 4. So 4f, 5d, 6p. And a way you can remember that is by remembering the block designation in the periodic table. So the first two columns shown in green here are called the s block. That's because you're filling s orbitals. The block here shown in red is the p block. You're filling p orbitals in their valence electron. And the center, the middle section, is the D block. They're also known as the transition metals, and that is where you're filling the d orbitals. Well, elements in the same group, the same column, that's also known as a family of the periodic table, have the same valence electron configuration. And that means they have the same similar chemical behavior. And you can see that in group 1. A very good example of that is how reactive group 1 is in water. If you throw these pure elements of lithium, sodium, potassium, if you throw them in water, you get a explosion. They're very reactive in water, and that is because of their electron configuration. So the electron configurations really correlate with chemical behavior, and that's why the periodic table is so useful. Valence electrons are chemistry. Let's try a practice. So write a set of quantum numbers for the 11th and the 16th electron in the chlorine atom. We'll do the 11th first. So chlorine will have a 1s orbital, 2s orbital, 2p orbital, a 3s orbital, and a 3p orbital. Okay, now we want to find the 11th electron. So we'll start adding. 1, 2, 3, 4, 5, 6, 7. Remember, that's Hund's rule. You go all unpaired in the p orbitals first. 8, 9, 10, and 11 would be in the 3s orbital. So what are the 4 quantum numbers for that electron? The principal quantum number would be 3. It's in a 3s orbital. The L value for that electron is going to be 0. And why is that? That's because it's an s orbital. What is m sub L? Well, m sub L can only be 0 because L is 0. There's only one value. And what about m sub S? It can be +1/2 or -1/2. Just by arbitrary convention, we kind of start with +1/2. So because that's the first electron in that orbital, we write +1/2. Okay, so that's the 11th. Now let's try the 16th. So I'm not going to label the orbitals. I'm just going to draw them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. This is our 16th electron. What are its 4 quantum numbers? Well, N again is 3. It's in the 3p orbital. L, now L can be, since it's a p orbital, L is going to be 1. M sub L now can be -1, 0, or 1. And because this is the first p orbital, just by convention, I would write that as a -1. I don't know if there's really I don't think there's a correct M sub L value for that. I think you could write that as -1, 0, or 1, but let's just say that will be -1, this will be 0, and that will be 1. let's see, m sub s now, it's the second electron added to that orbital, so it's going to be a -1/2 for the spin quantum number. So there are the 4 quantum numbers for the 11th and the 16th electron in the chlorine atom. Okay. Question 2. Using the periodic table on the inside cover of your text, so don't cheat and don't use this periodic table. Use the periodic table that does not have the electron configurations. Give the full and condensed electron configuration, a partial orbital diagram showing the valence electrons only, and give the number of inner electrons for the following 3 elements. Okay, let's start with calcium. So the full electron configuration for calcium. It's 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. And again, you're really going to want to have a periodic table handy when you're going through this lecture and trying to work through these problems. It's essential. And what does the condensed configuration become? Well, we look back at the previous noble gas, which would be argon, and our valence electrons are going to be 4s2. And what does the partial orbital diagram become? Well, that's simple. We just have 2 electrons in the 4s orbital. And the number of inner electrons, the partial orbital diagram, and the condensed configuration shows the outer electrons. So every other electron will be considered an inner. So we have 2 plus 2 plus 6 plus 2 plus 6. And that, if I did my math correctly, equals 18 inner electrons. Now let's look at zirconium. The full configuration for zirconium: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d2. And what does the condensed configuration become? You look back at the previous noble gas. That'd be krypton. So krypton, 5s2, 4d2. A partial orbital diagram. So we have 1, 2 s electrons, and then 1, 2 d electrons. Again, you add them to separate orbitals, keep them unpaired because of Hund's rule. How many inner electrons? If you count all the inner electrons up, you should come up with 36. Okay, finally, thallium. So the full configuration is quite long. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p1. Now, you may think writing something like that out is sort of overkill, but trust me, if you write enough of those out, you really get to learn the order in which the orbitals fill. It really reinforces it. In the condensed configuration, you can write that as xenon 6s2, 4f14, 5d10, 6p1. And that's how I would write it. Your book sort of tells you to move the transition orbitals, the f orbitals and the d orbitals. When they're filled, you can move them in. So you could write that as xenon 4f14, 5d10, 6s2, 6p1. I would consider either of those correct. I think sometimes you can even consider that without the f or the d orbitals entirely. You can consider them core, but I would prefer having those listed as valence electrons in our class. So the partial orbital diagram, we're not considering the F and the D for this. We're just looking at the S and the P. So there's 2S and 1P. And they're not going to count it up, but there are 78 inner electrons. And again, your book really considers those filled F, the filled F shell and the filled D shell as inner electrons. If I asked you to write a condensed configuration, I would really expect that you would include those in the condensed configuration because they're not part of the previous noble gas configuration. So if you're writing a condensed configuration, I'd like you to keep the F and the D electrons in it. But when you're doing considering valence electrons, outer electrons, you don't necessarily, you wouldn't need to. And chances are I wouldn't ask you for something that difficult on an exam. Okay. So we've looked at electron configurations of atoms. Now we're going to look at electron configurations for ions. So what are ions, first of all? An ion is an atom that has either gained or lost a valence electron. And usually this happens, a gain of an electrons or loss of electrons to get to a stable electron configuration of filled shell. There are two types of ions. One that has lost, when an atom has lost an electron, it becomes a cation. And a cation has a positive charge. And that is because it lost an electron, which has a negative charge, so it loses a negative charge and becomes positive. The second type is called an anion, and an anion is negatively charged because it gains an electron. It has an extra electron, so it becomes a negative charge. And if you look at the periodic table, atoms on this side are more likely to lose electrons because then they become a similar configuration to a noble gas. They have filled shells. And in a similar fashion, elements on this side are more likely to gain electrons because then they give a noble gas configuration. So how do we show that? Let's look at sodium, for instance. Sodium has an electron configuration of helium 3s1. Now if we take an electron away from that to form the cation, we're left with simply helium electron configuration. And chlorine. Chlorine's electron configuration is neon 3s2 3p5. If we add one electron, that becomes neon 3s2 3p6, or the same configuration as argon. So again, these ions are trying to become like noble gases. So if we, when we talk about two different elements that have the same electron configuration because one of them or two of them become ions, that is what's known as being isoelectronic. So isoelectronic means it has the same electron configuration. And here we see a magnesium losing 2 electrons, and oxygen will gain 2 electrons, and they both become like neon, the same electron configuration as neon. And here's a list of several different elements that can be isoelectronic. So if we look at transition metals now, transition metals tend to lose electrons to form cations. A loss of the valence electrons, in some cases d electrons as well, to achieve stable configurations. So if we look at iron, elemental iron has a electron configuration of 4s2 3d6. Iron 2+ loses 2 valence electrons and becomes argon 3d6, and that's really very important to recognize. The s electrons are the ones, the 4s, you fill before the 3d electrons. When you're taking electrons away from a transition metal, you take them away from the s orbital first before you take them out of the d orbital. The next iron can form would be 3+, and you take the one remaining electron is removed from the d orbital, and you get 3d5. And this is a particularly stable ion because the d shell is half filled. So you have 5 electrons in a d orbital. That's pretty stable. Okay, let's try some more electron configurations, now with a couple ions. So write the condensed electron configuration for the following atoms or ions. We're going to start with B. Okay, so B, iodine minus. So iodine minus would be krypton 5s2 4d10 5p6. And you can also write that as simply as xenon. Both of those would be correct as far as I'm concerned. Okay. C, we have rhodium. Rhodium's normally krypton 5s2 4d7, but we're taking, there's a positive 2 charge on it, so we're going to have to remove 2 electrons. And remember, for a transition metal, we take those electrons away from the s orbital before the d orbital. So those are both going to come from the s, and what we're left with is krypton 4d7. And now on to platinum. And I saved this for the end because this is another actually pretty tricky one. So what you might think platinum would be xenon 6x2 4f14 5d8. In actuality, its electron configuration, I'm going to write the F here this time, is 5d9 6s1. Sorry, that's probably confusing. I'll write that 6s1 5d9. And why is it like that? Well, if you think back to that electron or that orbital energy diagram, as you get higher and higher in principal quantum number, those orbitals get closer and closer in energy. And this is really where you get atoms, the higher the atomic weight of an atom, the higher the principal quantum number, you get these situations where you just can't predict what the electron configuration is. You need really hardcore calculations to be able to answer that question. So something like platinum, I wouldn't ask you that on an exam. These, again, when you look at the first 3-4 rows of the periodic table, it's very simple how you just keep adding electrons, very just like counting. But as you get lower, it really becomes much more complicated. Okay. Fourth practice problem. Select the electron configuration of iron 3+, also known as the ferric ion. All right, now for this one you have to remember the electrons, you're going to have to take out 3 electrons from iron. And remember that they first come from the s orbital. So you're going to take out 2 s electrons and then 1 d electron. And what you end up with is 3d5 configuration. And also remember that that's a half-filled d orbital, so that's a very stable configuration. Okay, moving on to 8.3, we're going to talk about trends in 3 atomic properties. And the important properties we're going to discuss are size, ionization energy, and electron affinity. So how does the size of an atom or an ion vary in the periodic table? So first we need to define what atomic size is. So atomic radius, it's calculated based on the distances between nuclei and bound together, that are bound together in molecules. For diatomic molecules, it's the covalent radius, metals, metallic radius, and for ions, it's half the distance between ions in the crystal lattice. So basically they're all the same definition. It's just you take the distance between 2 nuclei and you cut it in half, and that becomes an atomic radius, or the size of an atom. And here we have the graphical representation of that. We have a covalent radius in a molecule of chlorine. If we look at sodium metal, that would become the metallic radius. And an ionic compound is sodium chloride or salt. We have ionic radii. So more importantly, now, what are the trends in atomic radius? Well, atomic radii increase going down a group. And why is that? That's because the inner shell electrons shield the outer electrons, and that decreases the effective nuclear charge. So the more inner electrons you have, the better the shielding is, and the less tightly those outer electrons are held. So the outer electrons extend further and further from the nucleus, and thus the atomic size increases as n increases, as the principal quantum number increases. Atomic radii decrease going across a row or across a period. And why is that? It's because as you go across the period, your nuclei, you're getting an extra proton each step you take. And so that what that does is it increases the nuclear charge as you move across the row. And the electrons, you add an electron each time, but they're in the same energy level. So basically the same orbital as you're moving across. And the charge is getting stronger, so that's acting to pull those electrons in closer. So the atomic size is decreasing. So if we look at the size of the atoms on this abbreviated periodic table, we're not showing the transition metals. The transition metals don't all follow this same exact pattern. So we kind of leave them out of this discussion. But the size of an atom increases as you go towards the left side of the periodic table and as you go down. So another way you can remember this is that cesium is the largest atom and helium is the smallest atom. So let's try a question putting these sequences of atoms, picking which sequence is correctly listed in the order of increasing size. And the correct choice here would be 1. Now if we bring our periodic table in again, you can see the actual size of these atoms. If we look at the other choices, why they would be incorrect, sodium is further to the left than aluminum, so that would be incorrect. Let's see, barium is further down the column than calcium, so barium would actually be bigger than calcium. Chlorine is further to the right than silicon, so that would be correct. Chlorine's smaller than silicon. Silicon is lower than carbon though, just below it. So silicon's actually bigger than carbon, so that's incorrect. So what we're left with is choice 1. And if we look closer, fluorine is the furthest to the right. Bromine is actually below fluorine. Germanium is further to the left than bromine. And potassium again is further still to the left. So it's going to be the biggest atom in that list of 4. If we look at a plot of atomic size, this is kind of nice to look at. It gives you a good picture. So the smallest atoms in every row are going to be those in group 8A, the noble gases. And the largest atoms in every row are going to be those in group 1A. Now you can, if you look at the main group elements shown in black, there are no exceptions really. For the most part, at least in the first 4 rows of the periodic table, there aren't any exceptions. When we look at the blue, the transition elements, there are a little bit different pattern. And why is that? Well, that's due to the stability of the half-filled D shell. As they get closer to that half-filled D shell, they get smaller. But then as you add electrons after that, they're not held as tightly and they become bigger. This is not really an exception that I want you to really focus on, or you don't really need to know that for this class. So just any question that you're going to be asked about atomic size, you're going to assume that it follows the trend that the further down a group or the further to the left side of the periodic table you go, the larger the atom is. What about ions? We're talked about the size of atoms, but what about ions? Again, a cation is caused when an atom loses electrons from the valence shell. And when an atom loses electrons, it still has the same nucleus, the same positive charge, but it has less electrons. So that's going to decrease the radius compared to the neutral atom. So cations are smaller than their neutral atoms. An anion gains an electron, so it gains an extra negative charge. It still has the same positively charged nucleus, but it has more negative charge, so there's more shielding, and the electrons are held less tightly, so anions get larger than their neutral atoms. And we can see that in this figure. So if we look at lithium, sodium, potassium, their cations are all much smaller than their neutral atoms. And on the other side of the periodic table, fluorine, chlorine, bromine, their ions become much larger. So try a practice question organizing this correct sequence of increasing size for a group of elements in ions. So the correct choice is 4. And why is that? Well, let's look at some of the other choices. Number 1, we see argon. It's saying argon is smaller than potassium. And potassium 1+ is smaller than calcium 2+, and both of those are incorrect. Cations are always going to be smaller, and a cation that has a positive 2 charge is always going to be smaller than an ion that has a positive 1 charge if it's in the same row, and that's shown here. Calcium 2+ is smaller than potassium 1+. Right, let's look at choice 2. Chlorine minus is smaller than argon and smaller than potassium plus, and That's incorrect, because chlorine minus, as you can see, it's an anion. It's going to be bigger, much bigger. Let's see choice 3. Potassium plus calcium 2 plus. Potassium is not smaller than calcium 2 plus. Again, calcium 2 plus is a positive 2 charge. It's missing 2 electrons, so it's going to be much smaller. So that leaves us with choice 4. And if we look, calcium 2 plus will be the smallest ion in that group. It has a plus 2 charge. Then comes potassium, argon, that's not listed here, but it's a neutral atom, chlorine minus, followed by sulfur 2 minus. And sulfur 2 minus is just barely bigger than chlorine 1 minus, but again, it is bigger. So in this class, if you're given a question like this, you can always assume that an ion that has positive 2 charge is always going to be smaller than an ion that has a positive 1 charge. And if you're given an ion that has a negative 2 charge, you can assume that it's always going to be larger than an ion that has a negative 1 charge. And really, to do that, you should be given elements that are in the same row of the periodic table. And if I give you a question like this on exam, you can assume that they follow that trend, or they should really all be in the same row of the periodic table. Because when you start comparing atoms in the second row with atoms in the fourth row, then this gets a little bit trickier. All right, let's look at the second trend, ionization energy. What is ionization energy? Well, it's the quantity of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms or ions. And we can write a generic equation for this. X gas going to X plus gas plus electron. So the first ionization energy, you remove 1 electron, shown here using magnesium as an example. You can have second ionization energy, and that's where you take magnesium plus cation and remove another electron to give magnesium 2 plus. And the second ionization energy is always going to be greater than the first ionization energy. So what are the trends with respect to the periodic table of the ionization energy? Well, in general, ionization energy decreases down a column. And why is this? That's because less energy is needed to remove electrons from higher energy orbitals. As atomic size gets bigger, those electrons are shielded more, they're held on less tightly, you can remove them easier. Ionization increases across a row. And why is that? It's harder to remove an electron because that effective nuclear charge as you're going across a row is increasing. So those electrons are held onto tighter. And the ionization energy and atomic size are really kind of correlated in that way. The smaller the atom gets, the more it hangs on to its electrons. The larger an atom gets, the more shielding there is, the less tightly it's holding on to those valence electrons. And I should note that there are some important exceptions to this trend. Unlike atomic size, there's a slight decrease between s and p electrons. So between the s and p, and that is due to shielding effects. And we'll talk about a couple examples of these in a second. But the overall trend for ionization energy is opposite of atomic size, and that it increases across a row and up a group. So the highest ionization energy will be helium, and the lowest would be cesium or francium. We can show that again like we showed for atomic size in a graphical form. And now the highest ionization energy in a group will be the noble gas, and the lowest ionization in a group will be from group 1A. But you do notice on this chart, or you should, there are these exceptions to the general trend, where you actually have a step down. I think this is a better way of showing it, sort of a three-dimensional block graph. And we can see again that there's, you increase as you go across a row, but there's a couple points between, one is between the S and the P, where there's a step down. And there's another step along this, the transition between these two columns, where again you get a step down. And why is that? Well, here you're going from s orbital to p orbital. And it becomes much easier to remove one p electron and have a filled s shell than it is to remove one of a filled s electron or s orbital. So if you have two s electrons, it's much harder to remove one of those than it is to remove that extra p electron. So you have to remember the exceptions to the general trend occur between the S block and the P block. And that would be this transition here. The next transition, as we see here between nitrogen and oxygen, there's actually a small step down there. And why is that? That's because if we look at the actual electron configuration, nitrogen would be a 2s2, 3p3, and oxygen is a 2s2, 3p4. It's much easier to remove that 1p electron from oxygen, so it becomes a 3p3, again has a half-filled p shell. Remember that half-filled and fully filled shells are very stable. So it's much easier to remove that fourth p electron from oxygen to get to 3p3 half-filled shell than it is to remove one from nitrogen, that because it already has a half-filled p shell. Okay, let's try a practice question with these. List these atoms in order of increasing first ionization energy. We have lithium, sodium, carbon, oxygen, and fluorine. Okay, the correct answer is 2. So we have sodium is the lowest. It is on the far left side of the periodic table. And then we go in order across the periodic table. Lithium's next, then would come carbon, followed by oxygen, and finally fluorine. Fluorine's the farthest to the right side of the periodic table, so it's going to have the highest ionization energy. And just to remind ourselves what the trend looks like on the periodic table, we can see these plots. So we can also talk about successive ionization energies. When we look at this, if we look at, let's try lithium. Lithium has a pretty low first ionization energy. That's, you're removing the 2s1 electron, and then you're left with a stable core of electrons. But if you look at the second ionization energy for lithium, it's really high. And that's because the second electron you pull out of lithium will be a core electron. And those are much, much harder to remove. And if you look at this table, you see this red line, and that's telling you that there's a transition there between a valence electron that you're removing and a core electron that you're removing. The core electron are much, much harder to remove. And you can see that here, maybe a little bit easier if you use the three-dimensional bar chart. And this time we're looking at beryllium. So the beryllium has 2 valence electrons, and the ionization energies for those are pretty small. But when we get to the third ionization energy, when we're trying to remove a core electron from beryllium, it's really high, 10 times higher than the other 2 ionization energies. Our third trend we're going to look at is electron affinity. And the definition of electron affinity, it's sort of the opposite of ionization energy. But electron affinity is defined as the energy released as 1 mole of gaseous atoms gain electrons to form the gaseous anions. So with chlorine as an example, we would have chlorine gas plus an electron goes to chlorine minus. And that electron affinity, if you're curious, is minus 300, about 350 kilojoules per mole. Again, that's not a number you're going to have to remember, but it's just so you have something to compare it to. So what are the periodic trends with electron affinities? Well, they tend to be more negative as you move across a row and up a group. But for electron affinities, we really don't consider the noble gases because they have filled shells. So it's harder to add electrons to those. So the highest element in terms of electron affinity is fluorine. Let's look at some behavior patterns for ionization energy and electron affinity. We can say reactive nonmetals have high ionization energies and highly negative electron affinities. And these elements attract electrons strongly, and they tend to form ions in ionic compounds. They tend to form negative ions, so anions in ionic compounds. Now, reactive metals have low ionization energies and slightly negative electron affinities. So these elements lose electrons easily. They tend to form cations or positive ions in ionic compounds. In noble gases, very high ionization energies and slightly positive electron affinities, so they don't really gain or lose electrons easily. So let's go through the 3 properties we've gone through so far. Atomic size, remember, it increases as you go to the left of the periodic table and down a group. Ionization increases as you go up a group and across to the right on the periodic table. And then electron affinity, it increases going up and over, but again, there's many exceptions in electron affinity in this trend. So I really don't expect you to be able to answer any real questions on the trend of electron affinities. And finally, we're going to talk about section 8.4. And this section deals with metallic behavior. So what are metals? Metals are typically shiny solids. They have usually pretty high melting points. Metals they're good conductors of both heat and electricity. They also can be easily shaped. They tend to lose electrons to form positively charged ions, cations, and that we can say they're easily oxidized. So the loss of an electron means it's oxidized. And because they are oxidized, they are generally strong reducing agents. And I should say now that we're going to talk about oxidation and reduction later in the class, next week. So I don't think you really need to understand oxidation and reduction at this point. We're going to be learning about that later on in the class. So most metals form ionic oxides, which are basic in aqueous solutions. So if we look at trends of the periodic table with respect to metallic behavior increases as you go to the left side of the periodic table and as you go down the group. So if we look at group 5A, we start with nitrogen, which is a colorless gas. Then we have phosphorus, sort of yellow-red powder. And then as we go down this group, you see that the appearance becomes shinier and more metallic, more metal-like. So the metallic behavior is increasing going down this group. If we go across a period from sodium to chlorine, we see that the metallic behavior, the metallic appearance is decreasing. We go from something that's very shiny, very silver, to something that's brown, a brown gas. So this is a good summary, figure 8.22, that shows you the metallic content of a particular part of the periodic table. The nonmetals here are shown in this sort of yellowy color. The metallic elements are shown in blue, and what are known as metalloids are shown in green. And they're in the transition between nonmetals and metals. And then what's also kind of nice about this chart is it shows you oxidation number. So in group 1A, you can have a +1 oxidation number. That means these tend to lose 1 electron. In group 2A, you lose 2 electrons, and so forth. But you see that the metalloids can actually lose a bunch of electrons, or they can gain some. Again, these ion formations are really, they're trying to get to a stable noble gas-like configuration. So carbon, for instance, it can lose 4 electrons, and then it becomes much like helium, or it can gain 4 electrons. and becomes like neon. So we haven't talked about acid-base chemistry yet, but we're going to talk a little bit about the acid-base behavior of oxides. So main group metals form oxides, ionic oxides, that tend to be basic in solution. So that's shown here. Calcium oxide would be a basic if you put it in water. Main group nonmetals tend to form covalent oxides that are acidic in aqueous solution. So phosphorus oxide is acidic. And next time we're going to talk a little bit about what ionic and covalent, what those terms mean. So if you're unfamiliar with those terms, don't worry too much about it right now. We're going to be discussing that next time. And some metalloids can do one or the other. They can act as an acid or a base in water. And an example of that is the aluminum oxide. So if we look at the periodic trend of acid-base behavior of elemental oxides, we see that the acidic behavior increases as you go up a group or to the right of the periodic table. The basic character increases as you go to the left side of the periodic table or down a group. So that really completes our picture of periodic trends. So we have atomic size, ionization energy, electron affinity, metallic behavior, and as well as the acid-base behavior of the oxides. So that's all we have for this lecture. Next lecture we're going to be moving on to Chapter 9. We're going to be talking about Lewis symbols and bonding, the particular bonding models such as covalent bonding, ionic bonding, and metallic bonding.